This is going to be more of an overview of AlphaZero, the system. There's a bit of supervised learning, there's a bit of reinforcement learning. There's something for everyone here, and even some Multicollege research.
So it's a real pleasure today to have Alex Davies with us. He's been with DeepMind for some amount of time. I actually don't know very much about history. It's shrouded in mystery, but I know he's a wonderful engineer and has a really exceptional ability. He really understands mathematicians extremely well. And I'm absolutely delighted that he agreed to give us a technical history of AlphaZero today. So thank you very much, Alex.
You're very welcome. And yes, I like to keep my history shrouded in mystery, and hopefully my lack of understanding of mathematics in general is made up by my understanding of mathematicians to some degree, of working together with you, the mathematicians that we did for this work. But I thought an interesting talk to give to everyone here today is going to be a technical history of AlphaZero. So this is one of DeepMind's more famous machine learning systems that we built in order to originally learn how to play Go and eventually beat the world grandmaster at Go. And it's certainly something that has inspired a lot of people in terms of the possibility of deep learning and reinforcement learning. And with some of the ways that these systems are presented, even in the papers, you often kind of get the end result of what the system is and how it works. And if what you're doing is going through this seminar series and thinking about how can we use reinforcement learning or supervised learning in order to solve problems, it'd be very instructive to go back and see how was this actually developed, what were the steps taken that resulted in this system that can learn to play better than any human has ever played Go or chess or any other perfect information two-player board game in less than 24 hours on a single machine. So AlphaZero is the state of the art for board games. And there's been more extensions to AlphaZero since this, I guess, in the last 3 years, but I'm just going to kind of take for the purpose of this talk the progression up to AlphaZero, which addresses two-player perfect information non-stochastic games. So the examples that we will use for AlphaZero, and we'll see later on, are Go, chess, and a game called Shogi. I would highly recommend, if you haven't seen it, and I'm not just kind of plugging this because it's a DeepMind thing, this is genuinely an excellent movie. There's a movie about AlphaGo. It gives you an interesting insight into the kind of feelings behind what was happening in the lead up to the big challenge that we had against the Grandmaster Lee Sedol.
Go is the world's oldest continuously played board game. It is one of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lee Sedol.
A match like no other is about to get underway in South Korea.
Lee Sedol is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge.
The whole world is watching.
Can Lee Sedol find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Look at his face.
That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think there's something went wrong.
Yeah, it's made a mistake.
He's got to pronounce a miracle.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
So this was obviously a pretty hyped thing in the machine learning community at the time when this match came out. And in particular, you know, Go had been a very long-standing grand challenge in artificial intelligence, similar to the way chess was before the deep blue matches against Garry Kasparov. It was generally thought that the Go wouldn't be solved for 10 to 20 years around the time when this match actually happened. So I think both in the machine learning community, this was surprising that we were able to get these kind of results. And as you'll see, with conceptually techniques that are relatively straightforward or accepted now. And also this was a huge upset in the world of Go, where it was assumed that no grandmaster level Go programs would potentially ever be made. So the progression of this talk, I'll talk about 3 separate systems leading up to AlphaZero. So the first system was AlphaGo, the second was AlphaGo Zero, and then the third was AlphaZero. So I'll start with a brief history of AlphaGo. So what was the very first step towards this journey of having a general learning system that could learn to play board games? Now, hidden in the background, hardly hidden in the background of this slide, is a little dependency chart of all of the different versions of the models that were trained and subsequently went into the training of models further downstream. And this was all a very manual process that the team was engaging in. So this is a small snippet at one point in time, and this got a lot more complicated later on. So there was a lot of engineering and kind of manual tweaking that was going on in the background during the development of this AlphaGo system, and I'll describe a little bit about what that was and looked like as we go through this. So the first paper that really kicks this off and led people to believe that maybe we might be able to make a program to play Go was this move evaluation in Go using deep convolutional neural networks from December 2014. And so this actually wasn't about playing Go at all. This was about seeing whether you could train in a supervised fashion a neural network to predict what moves would be made in highly ranked human games. So there was a data set of 160,000 games from an online Go server called KGS. And from this, you can look at the board states and you can set up a supervised learning task, where in this case, what you're trying to do is for any given board state that occurs in any of these games, predict what move the other person would make next. And so this is a kind of nice task because it's a straightforward supervised learning task where we have a big data set, we have the inputs and we have the labels. And they were able to improve quite substantially over the previous baselines by using neural networks, because this is back in 2014, which was relatively early on in this phase of, if we just make big neural networks, it turns out they can approximate functions very well. And so I think they may have got, let's say, from an accuracy of around 30% to 40% or 40% to 50% over the previous best. So quite a substantial improvement. Not anywhere near perfect, but really quite good. And so I just illustrated, I'm calling this a policy network because this is going to be a policy network in a reinforcement learning agent. But you can just think of this as a general supervised learning task to begin with. And what we want a policy network to do is we want it to be able to give us a probability distribution over actions conditioned on a state. And so for the game of Go, a state is going to be a fixed board state. So it's going to be a board with all of the black and white stones that have been played thus far laid down on the board. And then the valid positions for next actions are any position on that board which doesn't currently have a stone. And so for any board state, what we want our policy network to do is give us a probability distribution over actions. So a probability distribution over all of the remaining locations on the board as to which one, for the supervised learning case, it believes a person would next play a move in. And so on the right, you can see an illustration of a Go board. And there, the kind of fixed black and white circles are stones that have been played. And then you can see some other circles which have numbers inside them. And this is essentially, within those, there's the probability that the network was assigning that is a move that someone would play next. So not all of the spaces are filled in because most of them have negligible probability. You can see there's a circled one in red, which is the maximum likelihood estimate of what action the player would take. So it's got 60% chance. There's another highly probable move on the right that says 35, and then there's a kind of smattering of ones with the probability of less than 1%. And so the way that this probability distribution is predicted is kind of on that diagram in the center, you start with the board as an input state as an n by n grid, and then we're passing it through several layers of a neural network and outputting effectively another n by n grid of real numbers, which we're then going to normalize to a probability distribution over the different moves. And as a matter of implementation, you would probably force it to be the case that it can't choose somewhere that already has a stone on it, rather than forcing it to learn that, which it could, but you probably wouldn't ask it to do that. The network that they used in that paper, I believe, was a convolutional neural network, although at different times, AlphaZero has had, I think, both a convolutional neural network or what we would call a residual network, which, if you haven't covered so far, is a kind of basic feed-forward network, but where there are also connections that skip over layers kind of arbitrarily from each layer is connected to potentially every other layer further forward. So once we have this policy, you could take this and you could play against it, right? You could just take a supervised network here and we could try and play against it. And if you took this policy network and I played against it, I'd probably lose. But that's only because I'm not a very good Go player. So there's two kind of sources of weakness for playing against this policy. Well, there's probably more, but we can kind of characterize two parts of the weaknesses of this policy network. One is that the neural network might not be doing a great job at the moment of generalizing and understanding, what actually is the true distribution over actions for a given state. And the second thing is it's learning to play from players that are pretty good but not great. So we have obviously a lot of online games from reasonably strong human players, but this isn't going to be anyone who's good because they would beat anyone on these servers. So this is in some sense learning to play the suboptimal moves that human players would make. So this is a kind of diagrammatic overview of what we're going to be looking at in AlphaGo. And so it uses two data sets essentially. The first is these human expert positions, so like the KGS data set. Ignore the rollout policy for now. We can talk about that later if we want to, but what we just talked about first was this P sigma, this supervised learning policy network, where we have a way of predicting the action distribution for a given state, trained on human expert positions. And then we're going to see that you can use policy gradient methods to improve the policy. So we can, once we have a strong supervised learning policy network, we can improve this using policy gradient to get an RL policy network. And then with a strong RL policy network, you can perform self-play in order to train a value network, which is also going to be important for how AlphaGo actually assesses the moves that it makes in the end. So one of the guys you saw in the video clip was Fanway. Fanway was either at the time the European champion or an ex-European champion, which is in some sense a strong Go player, but for anyone who knows much about Go, the European scene is not particularly strong relative to the Asian scene of Go. So they have DANs is how they rank professional Go players. So I think 1 up to 7 or 8 or something along these lines. And so I think Fanway was maybe a 1 or 2 Dan, whereas the world champion from China would have been a 7 or an 8. So with a difference that large, you would expect that they would beat Fanway in almost every game that they played. But we've got to start somewhere. And after the system was sufficiently good that it was able to beat all of the people who played casually or semi-seriously DeepMind, the first match we had internally was against Fanway. And the system was trained following that diagram I just showed before. So you start with a policy network that was trained from this fixed data set from KGS. You improve the policy network from self-play games using policy gradient, or in particular, an algorithm that people call reinforce. So let's talk about that very briefly. So policy improvement with reinforce is actually pretty simple.
Can you explain what you mean by policy gradient?
Sure. So policy gradient. So policy gradient is a training method, let's say, for reinforcement learning systems, where what we're going to do is optimize the policy that we have. So the policy was a neural network, and we're going to optimize that by gradient descent. And there are a number of different ways to do that. One of them is by using reinforce. And so I'll describe that particular one, and maybe that will become a little bit clear. But essentially what we're going to do is we're going to play games, simulated games with the policy network that we have. And then we're going to use these observations to try and maximize the expected win rate by playing under the policy. So I'll kind of step through what this first term here means. And yeah, I'll open up for questions after this so I can make sure that it's reasonably clear. So what reinforce does, we have this policy, which in this case we have parameterized by theta, which is going to take in our state and give us an action at every step. And if we were just to play a game with this policy, eventually we would get out to the end of the game and we would either win or lose. And we'll say that if we win, we get +1, and if we lose, we get -1. And what we would like to do is maximize the expected value of playing under the policy. So if we were to sample moves, from our policy and play them against some adversary, then we want to try and win as many times as possible. So we want to maximize the expected value of the F here, which is going to be our win or win-loss kind of value function. Sorry, not the value function, it's going to be the reward. And here, this PZ theta is the probability that we get a particular trajectory of a game given a policy that we have. And so what this kind of short derivation shows is that if we want to get the gradient of this expected reward with respect to the parameters of the network, we can estimate this by taking samples. So we can take samples of games where we're sampling from our policy, and we just need to be able to evaluate this F, so whether or not we won or lost in a particular game, which obviously we can do for a game of Go. And we have to be able to take the gradient of the log likelihood. So we have to look at all of the moves that we played in the game and then evaluate the log likelihood of those. And that's going to be really easy to do because the joint probability of all of our moves is just going to be the product of the probabilities of all the individual moves. And so the log of the probabilities is going to be the sum of the log probabilities for all of the moves that we made along the way. And so we can take a number of samples of games, large S, capital S samples of games, and then we can calculate this final quantity here, which will be, in expectation, the gradient of the loss with respect to the current policy. So that was the first pass attempt at explaining what reinforce is and what policy gradient is trying to do. But what we're effectively trying to do is, to summarize, take an existing policy, play games with that policy so that we get samples of whether or not we win or lose under that policy, and then train the neural network by gradient descent, which I'm sure you've seen is how we would generally train all these networks. And the way we get the gradient here is through this little formula, is by trying to maximize the moves that seem to be leading to winning games at a very hand-wavy level.
Alex, is it fair to say, I mean, one thing that might lead to some confusion is that reinforce does not mean reinforcement learning. And reinforce.
Yeah, I apologize on behalf of machine learning researchers and how they name things. The all caps reinforce is a name for using this technique for reinforcement learning. Yeah, this particular identity here is also called like the score function estimator, and it turns up in statistics in a number of different ways. But in machine learning, this is popularized under the name reinforce. And reinforce in some sense is nice because it's relatively straightforward and simple to implement for a game. There'd be different there's different ways we can do reinforcement learning for games, but in the case where you're happy to just sample all the way out to the end of a game, then, as I said, this is very easy. You sample all the way out to the end of the game, you see if you won or you lost, and you evaluate the log probabilities of the choices you made, and it's very easy to calculate this gradient. So finally, the last element is a value network trained on this final improved policy network. So a value network is in some sense simpler than a policy network. So this is just an estimate of how good a particular state is. And effectively, this is going to be the expected reward or the expected, say, win rate for a player being in that particular state. And to make this more well-defined, we could have trained a value network on the original data set to say, for a person who plays on KGS, given a random person who plays on KGS, would they be expected to win or lose from this given board state? But we have a stronger policy network now because we've improved it using this reinforce step. And so we're going to train the value network on that instead, because we're going to assume that that's a better player in some sense. And now from this better player, we want to get an idea of what is a good or a bad board state. Can we just look at a board state and evaluate it to say, I think this is I'm likely to win from this position or less likely to win from this position. And you can see that the architecture for this is very similar to a policy network, except at the end, rather than having a n by n number of outputs mapping to the number of actions we have, so you're going to have a single output, which is the expected reward for a player starting from this point.
Alex, can I ask a really quick question about that previous slide? This is probably super basic. One thing that I kind of struggle with is, any particular board state you're super unlikely to ever see it. And so your network is only going to see any particular board state like at most once. So what design choices do you have to build into the network to kind of get a sensible probability distribution in the first network or output in this network?
No, that's a great question. And that's kind of, often the fundamental question for machine learning is, ideally, we're not ever showing it the same board state twice. And so how are we actually training something that generalizes to new board states in some sensible way? The answer here is, I think it's actually quite interesting over the progression of AlphaZero. So I'm going to make the claim, which I'm fairly sure is correct, is that for this version of it, it was using a convolutional neural network. So you've likely seen this in the context of images. So anything where you kind of examples where you have local shift invariant, which is not strictly true for Go, but it's kind of true, I think, to my kind of weak knowledge of the game. So, there is certainly in the kind of strategy side of Go, there are little motifs that have meaning to players, that kind of small little local motifs. And it makes sense for human players to talk about these occurring in different places. And so it's reasonable to think that this kind of structural prior on what we're looking at that's used for images might make sense here. And for AlphaGo, they also did use some kind of handcrafted features that came from human experts around information about these kind of motifs and some other side information. So to briefly summarize it, they use a fairly standard architecture, which works well for locally shift invariant grids, convolutional neural networks, and then talked to human experts to add some features that they knew were relevant for playing the game of Go. Ultimately, one of the biggest empirical findings of this era, so of the kind of ImageNet era and of AlphaGo, was the fact that just the fact that neural networks turn out to be like a good prior, or that they train well and are able to learn these things and generalize in an effective way, much better than people previously thought, and seemingly much better than other techniques. So and I guess we'll kind of go back to that as I get onto AlphaZero, because to kind of tip the ending, at the end, they were able to get rid of all of the human information. So there was no extra information except for the board state. And the final version, I'm fairly sure, does use residual networks. So they actually got rid of the this kind of structural imposition that you have this kind of translation invariance. And that actually improved the performance. So you actually have these neural networks that say very little about what's going on in this space, except that except there's a compositional structure to the function. So as you've seen in these networks, probably that there's this kind of repeated application of linear transformations and nonlinearities that gives you this compositional structure to a function, and that this does generalize very well.
Thank you.
Yeah, there is an ablation. I hope there is with or without reinforced, because I wouldn't know off the top of my head, but yeah, we'll get a good sense of that coming up. So this was pretty expensive to train. This was used 176 GPUs, so not cheap. And the final piece of the puzzle here was to use MCTS. So to say, what we have now is we have an improved policy network, and we have a value network, which is trained on this improved policy network. And so we now have two sources of information from which you can imagine playing a game of Go with either. So I could take that policy network and I could just play with it. And I could just take the value network and I could play with that as well, because I could do a one-step look ahead from any board state. I could look at it and see if I think I'm winning or not. And then I could look at all of my next moves. I could see which one has the next value, and I could just follow that. And so with either of these, I could just use them to play the game. And again, they would probably beat me, but they wouldn't beat Fanway. And so what Multicollege tree search does, which was seen as one of the bigger innovations of AlphaGo, was to incorporate search as well as learning, and use both this policy and the value function together to ultimately make better choices about how to move. And so the core concepts behind Multicollege tree search are that you want to evaluate many interesting positions and actions, and then aggregate this information together to make better action choices. So rather than relying entirely on the neural network to do the generalization and just look at this state and see what happens, you might want to take advantage of the fact that we can do search and simulation to make better decisions. And this is, I think, reasonably analogous to how human beings do this too, when they're playing at least games like Go and chess, in that you could show a board state to a grandmaster and they could just look at the board and they could tell you if it's winning or losing, and they could tell you almost certainly where the good next moves are, but they still do sit there and stare at the board and kind of play forward to figure out what actually is the right move to make. So they would do some version of both kind of a heuristic feeling about the board, as well as simulating forward to see what actually would happen. Well, I will go into more detail on MCTS in a little bit. So that was mastering the game of Go with deep neural networks and tree search. So then this AlphaGo was then played at this match against Lee Sedol. They changed the architecture to be running on different accelerators, which is, I think, not super interesting for this audience. But one thing that you can see, which harks back to that original diagram I had on the first one of the first slides, is that this is the version that played Lee Sedol was version 18. And so what was actually happening in the background is they were constantly building up and improving this policy network and this value network by making small changes to the algorithm, having a strong player, playing it off against new ideas, and each time coming up with a stronger and stronger policy network. And so this was the 18th version that they had by the time they got to AlphaGo League. This is a picture of the machines that were running against Lee Sedol. And so there's a little plaque in one of the data centers in Google, which has a picture of the board state that it ended up winning against Lee Sedol. In this case, it was changed so that the policy network was being trained on a larger data set, I believe, initialized from a larger data set of Go games, TiGem. I can't remember the specific differences between that and KGS. And then the value network was now being trained on something different, which was from fast MCTS self-play games. So rather than simply playing out the policy network as before and saying, if I was playing my improved policy, what would the value be? Now it's looking at games where it's playing full Monte Carlo tree search. which is a stronger Go player, and then learning the value function from that. So we are looking at different games, larger games, to improve the initial policy, proving that, incorporating MCTS to then play against itself, and then use the value function that's trained off of the MCTS games. And then when it got to version 33.6, and in the matches against Lee Sedol, I don't want to give away the ending, but ended up winning 4-1 against Lee Sedol in what was a huge upset. And then went on to, Lee Sedol was one of the kind of acknowledged best Go players around, but he wasn't the current world champion. The current world champion was Ke, who they played in May 2017 and ended up losing 3-0 to AlphaGo. And what was very surprising from the outside, I think from the Go community, is that when they beat Fanway, the response from the Go community was that was very impressive, but he was only a European champion who is substantially weaker than Lee Sedol or any of these kind of Asian grandmasters. Fanway was a big upset, but there was still the expectation then that he was a little bit past his prime and that Ke was a lot stronger. And then when it versus Ke, then it kind of soundly beat him over the course of 3 games. And one of the reasons that this is so powerful is because it was continuing to improve every time. So the version that played against Fanway was weaker than the version that played against Lee Sedol, which was weaker than the one that played against Ke. By the time they got to AlphaGo Master, this is now running on a single machine. This is, I guess, when they moved to the ResNet that I was talking about. So they've taken away this, enforcing this convolutional structure. They now have a full iterative setup where instead of just doing this once through of learning the policy and the value, they're doing this iteratively. So you go through the step of generating 4.5 million games, takes a week. You train these networks on the Selfplay games for another week. You repeat, and you just keep going through this process. And as you do this, it just keeps getting better and better. So this is a bit of a performance comparison about what's happening here. And I don't think I have one actually specifically about the improvement that comes from Reinforce, but we can make a pretty good estimate of where that would be. Sorry, was there a question?
How important was the initial step of training with actual humans? Is that speeding up the rest? So if you would, is it just kind of helping the initial kind of point for your optimization that you're going to choose? Could you do it without and just, do your self-playing for longer? Would that also work? Or?
Yeah, I think there's a really important meta point that I think I'd love to get you from this talk, is that as we get to the end of this and we get to AlphaZero, AlphaZero uses no human information. It actually doesn't start from a learned policy. It starts from a random policy, and it ends up doing better. So it does the best, and it does better than it starting from random than it does from giving it human biases to start off with. However, from a systems design perspective, it took a lot of work and learning on the side of DeepMind of what architectures are correct. Exactly how do you set up the system in order to learn Go, which was made a lot easier by starting on a simpler task like training from the human data. And everything that we're seeing here in AlphaGo, directly as it stands, wouldn't have worked if you weren't initializing the policy from strong human players. But once the architecture was refined sufficiently so that this was all working, we'll see how they were able to start taking things away and eventually get rid of these human games entirely. So this gives you a sense of the comparative strength of AlphaGo in terms of the ELO rating against the kind of red are the previous Go programs that they had, which, as you can see, all weaker than the professional players. And so, yeah, Fanway was about 2 Dan professional, which is about the level that AlphaGo was. I guess that's a single machine version of AlphaGo. And then if you're allowing yourself to run over lots of machines, then you can improve that up to like 3,200, which is probably what was playing against Fanway. And I think a really nice plot here is to see what is the difference of using different combinations of the value network the policy network or rollouts. So for example, if you just use the policy network, you can see that you get to about 1500 ELO. And so that's already, that policy network would be the one that is improved. That would be the improved policy network. So that's not the one that's learned directly from the human games. That's the one that's after using reinforcement learning on that policy. And that gets you 1500, which is about the rank of a kind of 4Dan amateur. So that's looking pretty good, but certainly not world class. If you just use the value network, you do slightly better. But this is something that you might expect, because with the value network, if you're using that to play, you're actually doing a very small amount of search. You're kind of taking one step of the move away from the network having to do the work. Equivalently, you can think that, for a given board state, you do one evaluation of the policy network in order to decide your next move. You do substantially more computation with the value network, because for every next move, you evaluate the value. So you do a little bit better there. And then as you start to combine them, you're going up from 1500, which is a low ranked amateur, to 3000 for the full combination of this value network, the policy, and the rollouts. And then you can also see here the difference that the computation makes. So in terms of how many machines you're throwing behind this, you can do on a single machine, you can still do up to 3000, but you can get a little bit of extra performance if you're willing to throw a lot of compute at it, at this particular version. So once they got to this stage, the problem was that generating a new version of AlphaGo takes 2 weeks, because you got to generate games for a week, and then you've got to train the networks for a week, which is, as I said, they're very impatient, and this was really slowing down the rate at which they were able to improve the system. And so the next version that they worked towards was called AlphaGo 0, where, again, you're taking away this expert data, you're taking away any handcrafted features that they knew about Go, and that there's no special rules in search. So can you go from nothing to superhuman just by using this setup that they've learned works by starting from these human games? And so now there's this idea of integrated continuous training and self-play. So going from this kind of batch mode of improving slowly, of generating a bunch of games, learning from it, generating a bunch of games, can we try and make this a bit more of a continuous process? And as we said before, it used to take 14 days and 4.5 million games to make a single iteration. And so in 36 hours, AlphaGo 0 reached this performance in AlphaGo League, which was version 18. So you can imagine that's 18 times 2 weeks. So that's 36 weeks down to 36 hours. And then another 72 hours, we can defeat AlphaGo Lee 100 games to 0, and which was the Lee Sedol version. And then if you let that run for a really long time, you can actually end up being substantially better than AlphaGo Master, which is the one that beat KJ. So this is the kind of wall clock time that it takes in order to train all of these things. And this is also the number of games. So we want to be efficient both in terms of the wall clock time and also in terms of the number of games it actually has to see. And so AlphaGo 0 was already substantially more efficient, because rather than 4.5 million games per iteration, now, with 4.5 million games, you're getting to the best system that they had previously. And with a relatively small increase over that, you can get to a very, very high level. And so this is another kind of steps of improvement. And you can see the training curve of how reinforcement learning improves over time, also compared with supervised learning in that purple curve. So I guess the main takeaway here is this actually is now putting AlphaGo Master in context with AlphaGo Fan, so you can see just how much better that version of it was as an AlphaGo fan, and why maybe the Go community didn't think that it was particularly scary. And if Lee Sedol had versed AlphaGo fan, probably would have won substantially. But by the time it got to AlphaGo Master, it's very, very far ahead of anything that humans could possibly play. But again, you can see this comparison against the raw network for AlphaGo Zero. The raw network is now getting 3,000, which is pretty good. But that search is getting you from 3,000 to above 5,000. And so the final version, so this was mastering the game of Go without human knowledge. So it was exactly that question that was raised before. Like, do you actually need these initial training games? And it turns out no, and it's even better to do it without. But if we'd tried to build a system to do it from scratch to start with, I don't think we would have been able to do it. And so the final part to move from AlphaGo Zero to AlphaZero is whether or not you can take this, what's potentially now a general algorithm, which isn't using domain knowledge in Go, and does this apply to other games, so like chess and shogi? So this is just more pictures of hardware that these are running on. So a lot of these experimentations at least rely on a lot of hardware in order to run these games and to try out the different architectures about how this models could work, even if ultimately the compute required isn't that much. So AlphaZero can learn from scratch to play chess, shogi, and Go better than the best games and also grandmasters in all of these games. And I guess we'd probably be good to try and go through MCTS. Maybe I'll try and go through this. I'll see if anyone has questions, and then I'll go into maybe a little bit of an overview of MCTS since I have that later on in the slides. So this is just the ratings of AlphaZero against the strongest competing systems at these different games. So Stockfish in chess, Elmo in shogi, and AlphaGo Zero in Go. And so AlphaZero, by using, again, less information and like different small improvements that were made over time, AlphaZero beats AlphaGo Zero 62% of the time when starting with white, which is a pretty reasonable given how strong AlphaGo Zero was. And you can see that in chess, we'll win 29% of the time when starting with white, and draw most of the time when starting with black against Stockfish, since you have that advantage of starting. And yeah, this is just the training curves for seeing how that improves. So there's a kind of very quick improvement up to very, very strong play, and then this kind of slow, gradual improvement over many thousands of iterations. Yeah, maybe I'll just stop and check if there are any questions there before I go into a slightly more in-depth overview of AlphaZero's training and MCTS.
In these games, everything has a board. So when you say AlphaZero, are you talking? Does that include games where you don't know anything about the kind of array structure of the board? And if so, how would you work on what type of layers to use, which wouldn't have like 190 or 19 times 19 squared matrix sizes or something like that?
Yeah, no, that's a really good question. So no, AlphaZero itself focuses only on board games, effectively, I think. So that version of it is only going to be playing, as I said, perfect information. You can kind of see some board at all times. And you could probably, given it's a ResNet, you could have something that wasn't strictly speaking a board, as long as it had like some fixed width representation of what it was. If you could give it some reasonable fixed width representation, that would be fine. I mean, because this is because it's using a ResNet, it's not.
But it's convolutional?
I believe not. This is something I should probably double check. If I'm wrong, I will come back and tell you. But I was under the impression that if they actually moved to a ResNet, which is taking away all of the locality structure from the board. So
so it doesn't depend on having a square.
No, and in the case that I'm wrong, which I don't think I am, you could certainly swap that out. So actually with AlphaGo, the system, you can just take that network that you're using for your policy or your value which in the case of AlphaZero is actually combined normally. So you'd have essentially an input that takes your board state and then maps it to a latent representation, so some vector in Rn, and then we'll train a separate policy network that takes that latent representation to make the choice of the distribution over actions and your value function separately. And so you can just take any network that you really want that maps from whatever your input space is to a vector in Rn and plug it in there, and it would train very happily.
Hey, Alex, I have one question, which you might be about to answer. But I was just sort of wanting to hear a little bit more about like which part is like the policy network used for and the value network, and like, I guess, like at what point in playing the game do you use the tree search, or is this only for training?
That's a good question. So you definitely use it for playing, and in the original version, so AlphaGo, it wasn't used for playing. It was used for playing, and it wasn't used for training. So for training, it was only kind of doing what we described, and then when you play, you do this MCTS, which I will describe in the next slides. And then as you got to the later version, it was also used in training. But yeah, I'll describe that in a sec. All right, so AlphaZero. This is just a description of what I was saying before, where AlphaZero moved to this framework of continuous self-play and training. So rather than the original setup, which was inspired effectively from this idea that you have all of these, you have this data set of games, of human games that you learn a good policy and a value from, and then you can generate a new data set from your new strong policy to essentially replace that old data set. You can say, okay, we had a really good data set that got us a good policy, we improved that policy, and if we get that policy now to play a bunch of games, like 10 or 20 million games, now we've got a data set of 10 or 20 million games that we think are stronger than the original one. And so we can just now use that as our new data set with potentially we can also mix in, from the different versions data. But maybe that's a bit inefficient. We don't have to go through this whole big cycle, and we can just start training and playing games and constantly improving at the level that we're currently at. So you have now a bunch of jobs where you have sorry, when I say jobs, I mean like jobs on a computer, running self-play games against each other so that you're generating data about games constantly. And the way that happens is you're running MCTS on these hardware accelerators. So what happens during self-play here is from a board state S1, so you have a game tree that you'll play out. So we'll generate we'll kind of play forward in the game a little bit by using our policy and value network to move down into places in the game that we think it's going to go, similar to what you would do if you were playing. You'll play a move out, hypothetically in your mind, see how you think your opponent would respond to it, and kind of do this out to see where you think the good moves actually are. And the ultimate outcome from this tree is we will get a pi1, which is a kind of empirical distribution over the actions that comes from the tree search. This is essentially how often in the tree we've gone through any of the actions at the top level. So from state 1, our next action, we'll have this pi1, which is different than the policy network. And then we'll sample an action from this pi1 distribution to take us to the next state. We'll again get a new kind of pi distribution over moves that we think are good that come from the MCTS, that come from tree search. And then we'll go all the way out to the end of the game where we'll get the outcome. And to build out this search tree, they use 800 simulations. So you're essentially playing 800 moves forward in the tree to try and see what might happen. And then in order to explore more, one of the things that you need to take into account in reinforcement learning often is to make sure that you're not always playing optimally against your policy, because that means that you won't explore sufficiently into parts of the game space that currently you would never play with your policy, but might be good. And so they would sample the actions for the first 30 moves to make sure they're trying to both stay inside reasonable parts of the Go board state, but having some chance to see different kinds of games, and then playing argmax for the rest of the game. So just picking the best moves once you're sufficiently far down the game tree. And they also had to inject noise in the prior at the root in order to help exploration. So there's also some extra randomness that comes when you're picking your first move, which you can essentially think of as injecting uniform random noise to which move to take. And so in AlphaZero, these are what are saved during the game that we're going to train our networks against. So we have the pies, which come from MCTS, which are pretty good estimates of what the right choices it would be for a given board state, and then the actual outcome. And these games are constantly passed over to the training loop, where you take these games in, you're retraining your policy and your value networks. And AlphaZero, one of the ways it's slightly different than AlphaGo Zero is this policy network here is now not being trained, for example, by reinforce, where you would be playing this game out to the very end and then trying to optimize the policy so that you get a higher win rate. What the policy is now doing is it's trying to directly predict the move distribution that comes out of MCTS. We could spend a bit of time talking about why that is a sensible thing to do, or why that might be a sensible thing to do. But I'll kind of just leave some comments here that one of the trade-offs that you would have to make if you're doing reinforce is that you need to play the game all the way out to completion. So that is takes like a lot of moves, is quite noisy. If you're just taking a single Monte Carlo sample of an entire trajectory out to the end, or even many, you might need many of those trajectory samples in order to get a good estimate of the gradient. And we should be able to use the information that we know already about the board in order to not have to do this. And this is the basis of a lot of reinforcement learning algorithms, the idea that maybe we don't have to go all the way to the end. If I play out 10 moves into the future, I might then know from my value function that I've already reached an unwinnable position or an incredibly strong position. And we can sacrifice knowing what would have actually happened in the end of the game and playing all the way out to the end by leveraging the information that comes from the value and the policy further on down the game. That's a little bit like what this AlphaZero is doing here. The value is more straightforward. We're doing a similar kind of thing as we always did. We're just looking at the board states and trying to predict who is going to win. So the final thing, we'll just go through MCTS. So I kind of like this as a general intuition slide about why MCTS is a reasonable thing to do. So in what we would normally call queue-based methods, you do a one-step look ahead. So a queue value or queue function takes a state and an action and tells you how good is it to make this action from a given state. So this is actually slightly different than the policy and the value that we've had, but you can imagine using a queue value, which is essentially kind of go to the next state and then evaluate the value function of that state. And that's going to be our queue value. So you can think of it as this one-step look ahead, where you, in your current state, you take one step forward, you look at the values for the states one step ahead, and then you just select your actions by taking the max value. And so there's two observations here, which I think are pretty good ones to remember, which is that the real queue function is too hard to represent. So we are doing a good job when it comes down to it of representing this policy function, the value function. If you were to loom an actual queue function, the same kind of thing. But the real, true, honest to goodness versions of these functions are going to be too hard to learn. Potentially we can't represent them, or we can't get enough data to learn them, or for whatever trade-offs we're making, we really can't get the true version of it, but we can just get a good approximation. And the max operator is very sensitive to outliers when it comes to function approximation. So you can imagine it to be the case that maybe for all of your next step value functions, you almost always do a very good job. Your value function is very close to the true value for all of your value states except for a handful. And for those handful, they're higher variance because you haven't seen, like, they're off distribution. So they're from the kind of value, the kind of states that you don't often see as you play. Or they're part of, like, they haven't been optimized well as part of the trading for the network, and they, for some reason, it just does a bad job on it. And so maybe we imagine that we just add some noise to those states, and they might come in very underestimated or very overestimated. If you then aggregate by max, you're very likely to pick one of these outliers purely based on their noise. And this problem can kind of increase as you have more options, and as you have higher noise, and as you have a kind of larger chance that one of your objects is noisy. You might end up in this regime where even if you're doing a really good job most of the time, your max operator is often going to pick specifically the bad noisy examples. So what we can try and do to improve this is we're going to do multi-step look ahead. So don't just look one step into the future, look many steps into the future. Being selective on the trajectories that we evaluate, so trying to focus on parts of the game state forwards that we think make sense, and try and aggregate that information differently. Don't just use the max. So a quick run through what MCTS is doing for any particular state. So for any particular state, we've got all these one-step future states that we could head to. And the lines here are the actions that you would take, the move you would make to get from one future state to the next. So what information does MCTS look at? So at a particular state, we have a value for every node. So every board state has a value for a value function. And we're going to use the policy network as a prior for our actions. So we're going to have a probability that we take any action, as well as knowing the value for every state. And what MCTS is going to keep track of is a visit count for every board state that it goes to. And we're going to ultimately use that to make the decision of where we're going to make our move. For the value, the parent value should be the weighted average value of its children. So this is kind of an identity relation. If we have a value function which is saying my expectation if I play under the policy is that I will win this much, then if we actually expand out that expectation one level, it should be the expectations of the values at the next step under the prior for the actions under the policy. And in the same way, these yellow visit counts, the parent visit count is the sum of all of its children's visit counts. Because if you imagine playing down a tree, in order to get to one of the children, I have to go through the parent state. So we have a tree that we're slowly building up, and we want to expand that game tree. So we want to pick a node to expand and make an extra move to kind of build out this plausible paths of the game in the future that we're evaluating. And the heuristic that they use to do this is based on this idea of upper confidence bounds. And so in machine learning, there's this, generally speaking, in kind of reinforcement learning and related areas, is trade-off between exploration and exploitation. So trying to pick moves that you think are good, but also trying to pick moves that you know less about so that you can try and learn more. And so we want to pick something, moves that's promising, but also where little is known about it. It's kind of worth a whole lecture on it by itself. But the general gist of upper confidence bound methods are that you pick something based on an upper bound on how good you think it is. So in a really simplified example, you can imagine for any choice that you have to make. You have an estimate of how good it is, as well as maybe a variance of how uncertain you are about its goodness. And if you just picked the ones that had the highest expected value, you might be missing something. It might be the case that something which is lower, but for which you knew very little, was actually in the end the best choice. And so a very simple and effective heuristic in reinforcement learning and related areas is to look at an upper bound, an upper confidence bound. So in the case of the kind of fixed mean and variance, you could just look at ranking it instead of by its kind of estimated value, its estimated value plus some number of its standard deviations. And so you're essentially just being optimistic about what you don't know and looking in places where you think it could be good and bringing these down. And this is a modified version of this for tree structures, essentially. And I'll kind of skip this so we can just get through. We apply the selection formula from the roots. So we kind of go through picking actions that seem good, but also have high uncertainty. And you go down through the tree until you get to a leaf node. And then we can run our policy network and value network on this new leaf node, and then pass back up the counts of visits that we've made as we've gone through this tree. And I think as you saw on the slide before, they use like 500 or 800 expansions. So you'd end up with a tree that has 500 or 800 nodes, but which is a kind of arbitrary tree. So it might be focused down on a kind of small set of interesting paths, or it might be quite broad, depending on what the distribution of the policy looked like. So if it was very broad, the tree might be very broad. If it was very confident about a few areas, it might be quite narrow. And then once this is completed, you select the actions based on the visit counts. So this is what they were talking about trying to get around the max aggregation, is rather than picking the route that had the best values further down in the tree, we're going to pick the one, the subtree in which we spent the most time. I know I kind of rushed through that, but I think that might be the way to go for this morning. So this was a kind of very popular blog post, which is quite worth reading, by Rich Sutton, who's a very famous and long tenured machine learning professor, saying that it was very frustrating for many people in machine learning about how effective the search and learning are. So obviously there are a lot of different kind of views and techniques about machine learning and the tools to get us there. But in the recent years, in the last 10 years or so, kind of learning in the form of neural networks and deep neural networks, and also search, seem to scale arbitrarily. So the larger you make it, the more data you give it, the more search you do, the more learning you do. You just seem to be able to improve constantly in a way which is not limited by human intervention. So this is another, I guess, cut-off version of that final one that I showed, showing that essentially the improvements from search and learning are pretty comparable in this case. So you get 3,000 and 5,000. About half your ELO is coming from learning, and about half the ELO is coming from search. And so AlphaZero in the end was about, trying to solve Go, but then paring down to see what was actually needed when it came to doing this. And it turns out the things that were actually needed in the end were very few assumptions about the structure of the game that was being played. It was no human information. It was only self-play, these deep neural networks, and search. And those two things combined will get you straight from scratch to grandmaster level in Go, chess, or shogi. And yeah, I think I'll finish up there and give some more time for questions.
Okay, so just maybe a quick question, Alex. You had this extraordinary training curve. So you had reinforcement learning and supervised learning being compared quite a few slides back.
This one?
Exactly. So I didn't understand what supervised learning curve is there.
So for AlphaGo 0, I don't know off the top of my head. I assume that is Well, it's getting up to 3,500. So what is that doing supervised learning on? I'm going to take a guess that that's doing supervised learning on games played by AlphaGo Lee. Would be my guess. So this is probably just doing straight supervised learning on games that were played by previous versions of AlphaGo. Because at this stage with AlphaGo 0, they generated these really large data sets, and this idea behind what they were doing in AlphaGo was, every 2 weeks we make a big new data set, and like, this is our new data set of games. This is our new data set of games. And so my guess is that that's being trained in a supervised fashion on one of the later data sets of AlphaGo. And then the reinforcement learning is the AlphaGo 0 starting from scratch and just using reinforcement learning.
I think so. It's just training a policy network or something. So the difference, so I forgot, but AlphaGo Lee just has policy and value, but no MCTS, or it also has MCTS?
So AlphaGo Lee has MCTS, but I could go back on slides. I think it only uses MCTS for playing and not for training. So it kind of went through the MCTS just at the end. If you have a value in a policy network, you can use them to put the tree out and then decide what move you're going to make. And so for AlphaGo Lee, it's just taking these policy and value that we've trained separately to do that. And then subsequently, they changed to this model of trying to train the policy to replicate what MCTS says, rather than trying to directly improve it with reinforce.
Thanks a lot. So there's a question from Josh in the chat. Are you able to make any comment on AlphaStar and how it differs from AlphaZero?
Yeah, sure. So there's a lot of differences between the game of StarCraft and Go. Obviously, the big ones are that it's not a perfect information game. So you've got the fog of war. You can't tell what the other player is doing. There is maybe a lot more structure and long-term dynamics. It's harder to see what's going on. The action space is a lot bigger. Everything is a lot harder. So the system that was used for our AlphaStar was independent from AlphaZero, but obviously there's a lot of overlapping techniques that were used in both. One of the big challenges in AlphaStar was looking at the kind of dynamics, like the meta of the game. So for people who play StarCraft, there's a strong idea of a meta. So like, what's the current way that people play and what are other people likely to be doing? And if you find one strategy that works really well, then you'll be very exploitable. So people can just learn that this is the one thing that you do. And then there's a kind of meta game that's being played out about what strategies a particular player is likely to play and how you compensate for that. So that was one of the big challenges that they had to overcome in AlphaStar, was how to train populations of agents. So rather than just having a single Go playing agent like they do in AlphaGo, one of the big parts of the AlphaStar system was ensuring that they train quite a diverse population of agents so that you can be sure that you are playing well against any strategy as opposed to just whatever the current optimal strategy is. What else is interesting about AlphaStar? I think the other interesting thing about AlphaStar was that that is also one where I think it's the case that the state of the art still requires human demonstrations. So to kind of follow our story, I think we would hope that kind of start somewhat randomly and just learn how to play StarCraft by playing it. But I don't believe that any of the agents that we have at the moment can effectively do that. It's just too hard to get started in StarCraft. You can imagine that if you play enough games, if you play kind of randomly in Go, it's still sufficiently constrained that maybe you're going to start to learn just enough to get yourself on the right track. It seems to be harder to do this in StarCraft. So you can imagine that if you start and you don't know anything, you can have your drones or your SCVs just kind of walking around in little circles and you're just going to lose every single time. It's going to be very hard to start down on the right track if you haven't seen at least a couple of examples of someone playing. So that is one place where we can't do it from scratch yet.
Yeah, that was a great answer. Thanks. I'm wondering, when you talk about different agents, does that amount to kind of just like you've got different value and policy networks and you kind of just like go into one of them depending on how you see that the opponent is playing, or like, is that kind of what you meant? Or
yeah, essentially you could think of a different agent as, yeah, just a different value and policy network that have been trained maybe by seeing different games or in a different way, and then you can choose what to do with those. Yeah, I guess in training you can randomly select different types of opponents to play against. And if you saw any of the Alpha Star matches, they're I think in the end what they had was different Alpha Star policy and value networks that kind of played different strategies. So it would have one policy and value that learns to play with some certain set of units in a certain way, and then if you were playing with a different one, it would try a different kind of strategy. Or certainly have like very strong preferences for the types of units and play style that it had.
Thanks.
I just had one question following Josh's, which is the other difference with StarCraft is that the top players are, making like 400 actions per minute or something. Like pretty like big technical challenges, and getting something that can perform like that.
Yeah, that's a really good point. So you're also playing in real time at a much higher rate than you are for Go. And so in this case, we had more of the opposite challenge in trying to make sure that it was a reasonably fair comparison against the top StarCraft players, and that you can train a policy that's just able to do ridiculous micro where it makes 2000 pixel perfect actions per second, and a human can't replicate that level of hand-eye coordination, and it's just really not fair. So they had a really quite good system to limit the number of actions per second that it was able to make down to like both below the average of what a human would be doing, and also so that its peak. Originally, I think they only capped its average numbers of like its average moves per second to whatever the human's average is. But what it would do is it would kind of play very chilled out for a little while, and then during very intense battle scenes, like ramp it up to super human speed. And so they eventually put a cap on both the average and the max, so that you couldn't really exceed, in theory, what a human would be able to do. And I think it seemed reasonably accepted that as it was playing at the end, it was certainly very good at micro, but was not relying exclusively on that as a way to beat the grandmasters. We didn't end up having any problems running the networks fast enough to make these decisions. Like, in the end, that's just getting someone to sit down and optimize the system so they can run pretty quickly. But yeah, actually we end up having more problem on the other end.
Ask a quick question about the chess comparison. You had that graph where you're comparing, I guess, AlphaGo with Stockfish, and it beat it, but then it kind of flattened out. It looked like it reached a limit. And if you kept on searching and learning, do you expect to get better and better, or is there really some sort of limit that it was reaching? I mean, it kind of going back to that quote that you had up.
Oh yeah, like okay, if we really kind of put all the resources into it, could we get better than it was reaching there? That's a good question. I think I'm not sure how much they ever really pushed those limits. I think if you look at the training curves, you can kind of see like it looks like AlphaZero is capped out at this stage. Go keeps like improving a little bit just towards the end, and if you rolled this out for another million steps, I guess maybe you're still getting a small amount of improvement, but I think they do empirically hit a wall somewhere. But I don't honestly think that they've gone much further. Like I don't think they've tried to just make the network heaps bigger and just like throw more and more resources at it, just because there's not a lot of further game in that direction, I guess, to see. I guess the only thing to estimate once you get that far out is like is it the case you can always force a draw in chess from white, or is there a dominant strategy? I guess that's an open question in chess, so maybe you can get like closer to that, but I don't know if they've really pushed it to the absolute limit.
Thanks a lot, Alex. Really fascinating talk.
Great, thanks so much for having me.